So let's now go to problem 10.9. This is a classic. I have here an angle alpha, and here an angle beta, a rope, and here I have a mass m2, and here I have a mass m1, and here I have a pulley. The pivot of the pulley is frictionless, but the pulley itself has a radius r, and it has a certain mass m, so it has a moment of inertia in rotating about its center c. There is no slip on the pulley, so I can again use that alpha, which is omega dot for the pulley, equals a divided by r at any moment in time. Now I have three options, three possibilities. Either a on the right side is down, or a on the right side is up, or a is 0. And it is by no means obvious to predict what will happen. You will have to know m1, you will have to know numerical values for m2, for alpha, for beta, for the kinetic friction coefficient and for the static friction coefficients to decide whether it will accelerate like this, or whether it will not accelerate at all. Let us try to make diagrams. This force is m2g. Then there is T2. And now I'm going to make the assumption that it's going in this direction, accelerated in this direction. If that's the case, then the frictional force must be upwards, because it's sliding down. I can decompose the force of gravity in this direction, which is m2g sine beta, and I can decompose it in this direction, which is m2g cosine theta. So the normal force, N2, equals exactly in magnitude the same, equals m2g cosine theta. And I can do exactly the same here, except that if the object is accelerated downwards, that the frictional force here is in this direction. So here I get m1g, I get here tension T1, I get here a normal force N1, which is m1 times g times cosine alpha. In a similar way, I did that here. I now get a frictional force, which is a maximum value here. It is in this direction because the object is going to be accelerated in this direction. That has been my assumption. And then there is the component of gravity, which is m1g sine theta. I actually should have put this one in blue because it is a component of the real gravity. So only the red forces are the ones that are the forces acting upon it, but this one can be replaced by these two. But since this one eats up this one, we're only dealing with this one, and this one. Very well, so now we are ready to set up our differential equations. Quite a job actually. For object number 1, I have T1, which is, I call that the positive direction, minus this one, which is m1 g sine alpha, minus mu times m1g cosine alpha. That must be m1 times a. That's the acceleration along the slope. For object number 2, you can check this now, m2g sine beta. This is now obviously the positive direction. If this is the positive direction, this is also the positive direction. All the other forces are negative. T2 is up, so that's negative. Minus mu times m2g cosine beta equals m2 times a. So this is my equation number 1. This is my equation number 2. I now have here the pulley, point C, radius r. The pulley experience here a tension T1, and it experiences here a tension T2. So I can write down for the pulley that T2 minus T1 times R, that is the torque. T2 is clockwise, so it's positive. T1 is counterclockwise, so that's negative. That is IC times alpha. I about this axis of rotation times alpha, but I'm going to get rid of my alpha, so that is I relative to point C times A divided by R. And this is my third equation. I realize that every time where I have mu, I should really have written mu k, but I'm a little lazy, so I write down simply mu. Notice that I have three equations with three unknowns. I have T1, I have T2, and I have A, and so I can solve. And the solution is not all that difficult, except that now, and this is crucial, my A must be positive. If my A is not positive, then my whole solution is wrong, because the directions of the frictional force I have adjusted in such a way that it's only correct if indeed the acceleration is that M2 is accelerated downwards. So you solve for A, and A better be larger than 0. If A is not larger than 0, then your solution is wrong. I massaged it a little bit for you. When A is larger than 0, you can express that in terms of a mu if you want to. It's nothing special, it's nothing new, it's the same thing. And mu then must be smaller than M2 sine beta minus M1 sine alpha divided by M2 cosine beta plus M1 cosine alpha, and that is only then the case if A is downstairs. So this must be met. Now let's assume that the acceleration is in this direction. I now have to redo the whole problem, and I can leave all the forces as they are, with two exceptions. I must flip over the frictional force of 1. This frictional force now is in this direction, and this frictional force is now in this direction. And I have to rewrite the differential equations accordingly, and I have to solve again for A, and it better be now so that A is larger than 0. Otherwise, my assumption would have been wrong, and my frictional forces would be in the wrong direction. Now, when I do that, I find a different criterion for mu. I've expressed it in terms of mu. And now I find M1 sine alpha minus M2 sine beta. It shouldn't surprise you that the upstairs changes sign, and the downstairs is exactly the same, M2 cosine beta plus M1 cosine alpha. In all other cases, that this is not the case and that this is not the case, A equals 0, and the frictional force will be in general smaller than the maximum frictional force and could even be 0. I have chosen a particular example. I have chosen alpha equals 30 degrees. I have chosen beta equals 5 degrees. M1 equals 3 kilograms. M2 equals 10 kilograms. And I have chosen for mu, which is really the kinetic friction coefficient, 0.04. Well, the question now is it being accelerated like this on the M2 side, or like this on the M2 side, or is A equals 0? Well, what I did was, I said, let's calculate M1 sine alpha, let's calculate M2 sine beta, let's calculate M1 cosine alpha, and let's calculate M2 cosine beta. I substitute these numbers in. If I didn't make a mistake, I find plus 1.5, 0.87, 2.60, 9.96. Let's first evaluate the situation whether perhaps A is in this direction. In other words, is mu smaller than 1.5 minus 0.7 divided by 2.6 plus 9.96? And the answer is yes, because this answer is 0.05, and the actual friction coefficient is 0.04, and since 0.04 is indeed smaller than 0.05, the acceleration is non-negotiable, will be in this direction. Is it possible somehow that if we adjust mu, that A would be in this direction? And the answer is no. Because if you look at our criterion, what mu should be for A to go down, then you would need 0.07 minus 1.5 divided by 2.6 plus 9.96, and this is smaller than 0, this is negative, and so this has no physical meaning, and so this is not meaningful. If you take mu static equals 0.1, the only conclusion I must draw is that A must be 0, because I don't meet either one of my conditions. I don't meet the mu condition for the acceleration going downhill, nor do I meet the mu condition for the A going uphill. And so I want you to work on this a little bit. I'll help you. If the pulley is not rotating, T1 equals T2 equals T, that you can use. And I want you to calculate now what the frictional force 1 is, and what the frictional force 2 is, and what T is. And what you may find, to your great surprise, that this combination is not unique. Nature has several possibilities of doing this. In other words, there are several values of T that are allowed that meet the condition that A is 0. The only thing that I can tell you, which may interest you, is that always will you find that the frictional force 1 plus the frictional force 2 is always the same, and I believe, if I don't have that mistaken, that it is always 6.3, but you better check that. But nature has various ways of solving this problem. It's not one unique answer, not so intuitive. Now I have an interesting problem for you. I want you to try this at home. This is a yo-yo. The yo-yo has an inner radius r, 1, and it has an outer radius r2. I attach to this yo-yo a string which is wrapped around the inner core, and I'm going to pull, and I'm going to pull at an angle alpha. If alpha is small enough, the yo-yo will come in this direction. If alpha is large enough, the yo-yo will move away from me in this direction. By no means so obvious, but I will show it to you. And I want you to prove it at what angle, depending upon R1 and R2, this is going to happen. I have here a box. I have here a yo-yo. And I'm going to pull at a very small angle alpha. And what do you see? The yo-yo moves in my direction. I'm now going to increase the angle alpha substantially. I'm going to pull again. And what do you see? It moves away from me. Isn't that interesting? So depending upon the angle alpha, the yo-yo comes to you or goes away from you. There has to be friction here. Do it in your dormitory. You can do it on the floor, and you'll be amazed. But what is more important than anything else, what is that angle of alpha at which the transition occurs from moving towards me to moving away from me? I'm going to watch my tape now. I have 1 minute and 5 seconds left, and I will take out all the slips of the tongue and all the slips of the pen. Over for now, but not yet out. In problem 10.9, I don't know why, but all of a sudden in the drawing, I introduce an angle theta, which of course shouldn't be there at all. And so twice will you see in the drawing that I say cosine theta, which should in both cases be cosine beta, and once do I say sine theta in the drawing, which should be sine alpha. But in the algebra I did it correctly, so there's nothing wrong with the solution, it's only the drawing, which is not quite kosher. Okay, well, that's all I have to add. The other slips I think you will easily be able to correct for yourself.